Good. Okay. So let's start the class. So as we discussed previous times, sometimes this algorithm, this idea of embedding an graph into trees is like a very general framework, but it does not give. It gives us Lagrangian approximation and say number of vertices, and we cannot do much better than that. So the idea is that what about if the graph has some special structure, like it is planar graph or like bundled genus graph, or essentially the graph that they may have. We can maybe draw them in the plane, but maybe they have a few crossing. And more generally, we talk about H-minor free graph and bundled arboristic graph. These are the sparse graphs that we are considering. So we talk about this bidimensionality theory as like a general approach that you can get lots of results, both in terms of structural results and approximation algorithms, and like approximation algorithm generally 1 plus epsilon approximation, as well as fixed parameter algorithms. And so I just meant going quickly on that, the bidimensionality is that if parameter k is minor bidimensional, if it is closed under minors, if you take the minor, the size does not go up, and it should be large on the grid. So essentially, the grid R bar R grid should be omega R square, or in general, it can be f of R, but this f of R then appears in the running time and other structural results. And we talk about vertex coverage, a special case of that. I mean, it's an important version. There is a contraction version, as we mentioned. The contraction bidimensionality is somehow introducing the contraction theory in parallel with minor theory. And we discussed that the contraction is coming essentially from dominating set problem, which is essentially set cover, and is a very like computer science type of things, theoretical computer science things. So that's the thing that this was the whole idea of the only closed under contractions. So again, parameter k is closed under contraction if k, and k is generally parameter k is the solution to some optimization problem. If k does not increase when contracting edges, and it should be large on the grid or grid-like graph. And that was important that for dominating set, if you, this was the whole idea essentially, that for dominating set, okay, so yes, so that was the thing that we had it for dominating set. We had this property that if you are deleting an edge, because in the dominating set, every vertex either should be in the dominating set or a neighbor of that should be there. But if when you delete an edge, then you may need to actually increase the number of dominating set to cover both this vertex and this vertex. And that was the whole idea of this contraction bidimensionality, and that we discuss. Now, good. So just see this one. Okay. So, what was the theorem that we have it? Okay. So the theorem that we had was these things. Okay. And so and this was the thing that we talked, that if a parameter, so this was a thing that if a parameter K is bidimensional. Bidimensional means minor or contraction bidimensional. Then there is this bound parameter Treewidth bound that the Treewidth of this graph would be bounded by square root of K. And here we were assuming that we talk about large on the grid. So if you remember that, there we are assuming f of r is actually r square or omega r square. So then we get square root of K. In general, if it is general f, you will get O f minus 1K. So we had this assumption that we had this assumption that the function on a grid or a grid-like graph should be at f of r large. If f of r is r squared, then we get square root of K. If we had a general f of r, then we get f minus 1 f inverse of K. And again, the idea was simple that we discussed if you have a large Treewidth, because of the graph minor theory, we know that we have a very large grid, and then it means that then you should have very large K. So it cannot be, so in some sense, the Treewidth should be bounded by this K. And this is very important that we will talk about. So this is essentially the base of bidimensional. Again, it was simplified a lot from the previous works, but this is the nicest one essentially. Now, we discussed about this one, that if a parameter K is bidimensional and it's then there is a and there's a fixed parameter tractable algorithm on graph of bounded Treewidth, the running time would be h of Treewidth n to the order 1 time. And again, this happens for lots of problems, and h of Treewidth generally is just 2 to the Treewidth. Then we have a sub-exponential fixed parameter algorithm with the running time h of square root of K. Again, this square root of K would be h of f inverse of K n to the order 1. And typically, this becomes 2 to the square root of K n to the order 1. These are the results that we have it for lots of these problems, like feedback vertex set, dominating set, vertex cover, and lots of other parameters. And this algorithm is very simple, essentially. We are just running a bounded Treewidth algorithm. So this is the whole idea, is that we know that the Treewidth of this graph is bounded by square root of K. So just essentially obtain an algorithm to find the 3D composition of this width. And as we discussed, the running time of this algorithm would be, you can get 2 to the Treewidth algorithms n to the order 1 to get a constant factor approximation for Treewidth. This is exponential, but it is, I mean, if you want to get polynomial, then that's the result that I have mentioned with James Lee and Polynomial we had it. But if you want to just get constant factor, you can afford to pay this one to get a constant factor this. And on this 3D composition, you just solve the problem using dynamic programming or other things, using this assumption that we had this. So that's for fixed parameter. So as a result, for vertex cover and feedback vertex set, we have sub-exponential fixed parameter algorithms for any graph family excluding some minor. So this is the result that we have it. This was only known for vertex cover on planar graphs. And there were few works. Each of them, if you read these papers, some of them 30-page paper, to just essentially get these things. But here, if you are doing connecting the dots correctly, he said that, okay, we have this one, we are just in all of this. Again, the whole idea of bidimensionality is that if the size of K is the solution size for some optimization problem, that we can relate that one directly with the Treewidth. And the Treewidth is at most square root of K. When you relate it, then all of these results become essentially very easy or almost trivial, essentially. Now, another thing which is very interesting is this one, that this is actually more exciting, and there are several follow-up works on that one as well. If a parameter is bidimensional, it is, again, this assumption that we have fixed parameter tractable on graphs of bounded Treewidth, which means that the running time should be h of Treewidth n to the order 1. And there should be order one. This is also important. Order one approximable in polynomial time. Actually, for some of these instances, even log n approximable, it works. And it should satisfy some separation property. Separation property is some kind of, it happens for lots of problems. And there is a revision of this version. We originally defined the separation property, and then there was some more, relaxed version of that. And there is, I think, the final version. Also, we worked on it for the journal version, and we have a clean one. But I will talk about it. So essentially, the conditions are very similar to the previous things. We have the bidimensionality and fixed parameter tractable. And these two other things, it should be order one, as I mentioned. Lots of cases, order log n even is enough. And then it should satisfy this separation property. Then this problem has a PTAS, which essentially means 1 plus epsilon approximation for any epsilon greater than 0 in time h of 1 over epsilon n to the order 1. In any graph family excluding some minor. So again, this is like essentially hammered. We say it is bidimensional, then we can get 1 plus epsilon. And as I mentioned, lots of these algorithms we obtain for essentially for that goes for planar graph, bounded genus graph, H minor free graph, and several of them actually you can also generalize it to bounded arboricity. And as I mentioned, bounded arboricity and this kind of bounded expansions are the two important things that we are considering when we talk about a sparse graph. So if you want to solve a sparse graph, means that the graph that has linear number of edges, then these are the expanders, and the bounded arboricity graph, which essentially H minor free graph, planar graph, are the one that you should consider. Good. As a corollary of this, we get for vertex cover and feedback vertexes, we have a PTASs in any graph excluding some minor. And this also, it was previously known for vertex cover for any special graph, not for general graphs, essentially. This also, you can get it for dominating set and lots of other problems. So this essentially for any problem, which is minor or contraction bidimensional, if we have these conditions, then we can get a PTAS that these conditions are, some detailed version of the things, the requirement that we need, but it happens for lots of problems. Good. One consequence of this, essentially this theorem that we have it, is especially is this Treewidth bound that I have mentioned. And if you remember, we talk about several parameters. So in particular, we talk about vertex cover and feedback vertex set. So feedback vertex set is the one that you want to kill minimum number of vertices such that there is no cycle in the graph. So these problems were minor bidimensional. And two other parameters, for example, like dominating sets. And the diameter of the graph even. These were contraction dimension. And again, I mentioned that even just the fact that the diameter is a contraction bidimensional and these things, you could improve some bounds that was exist for local Treewidth from 2 to the R to the optimal bound of linear in R. So it's such an improvement, essentially, just this particular thing could give us, essentially. Now, this is the important thing. So we knew that for every bidimensional parameter P, the Treewidth of G is at most square root of P of G. So this parameter P of G, if it is large on the graph. Now assume that P of G is the number of vertices in a graph G. So in particular, if you consider a grid of size R times R, then what is the number of vertices there is R squared. And this is a minor bidimensional, actually. Now we have this one. For any fixed graph H, every H minor free graph has Treewidths at most square root of 8 times n. So this is the important things. This is the and this is the one that we are using it essentially to get a PTAS as well. So we know that for any linear free graphs, the Treewidth of this graph is at most square root of 8 times n. This is actually square root of 8 times not n, square root of 8 times n, which is essentially order square root of n. So for any H-linear free graph, we know that the Treewidth of the graph is at most square root of n. So planar graphs or H-linear free graphs or even grids, they don't have bounded Treewidths, but the Treewidth instead of n, that as I mentioned, it can happen for clique, we know that it is at most square root of n. So sparsity helps a little bit, but not much. It's a square root of n. One important result of this essentially is 1/3, 2/3 separator. What's the meaning of that? It means that for these H-linear free graphs, you can there is a vertex set whose removal leaves no component of size larger than 2n/3. So there is always, this is a separator theorem. So there is always a small number of vertices in the order of a square root of n. But if you remove it, you can essentially have the whole graph into 2 components, such that the size of each of these ones is at most at least 1/3 of n, and at most 2/3 of n. So that's the definition of a separator. So and why is separator is very important? The same reason that I have essentially mentioned for bisection. So if you can get some vertex set, a small vertex set, and you will remove it, and the graph has essentially each of these vertex set that you have is going down by a constant factor. In this case, at least 2/3 they are going down. It means that you can do divide and conquer, and the depth of your algorithm would be at most log n. So that is very important. Otherwise, I mean, the depths can be as large as n, and that is not good. So separators are super important for divide and conquer algorithm design. And this theorem essentially, it says that the Treewidth should be at most square root of n. And when the Treewidth is at most, when the Treewidth is, whenever the Treewidth is v, we can show that there is a separator of the same size as well, or order v. So there's a very close relation between separators and Treewidths. In particular, actually, if you have a good algorithm for separators, the way that you obtain this kind of Treewidth composition are via finding vertex separator. That's the paper that we had. That we had these things, this square root of log opt, as I mentioned, where opt is the size of the Treewidth for the graph, that use the concept of vertex separator. So Treewidth and vertex separators are very correlated. And as I mentioned, so if we know that Treewidth is at most a square root of n, it means that there is a vertex separator of size. Now, what is the interesting thing? This is the interesting part. The fact that, so why bidimensionality helps? So some of this actually we knew before, that, like, for example, Treewidth or the size of the separator for H-linear free graphs even is the square root of n. But the one that essentially bidimensionality helps is that it relates the Treewidth and thus the size of the separator. It relates it with, say, square root of the size of the parameter. What's the meaning of that? It means that if your graph has for example, a dominating set or vertex cover of size at most k, then there is a separator of size square root of k. This is super important. Why? Because generally this is the idea, as we will discuss, that whenever you have a good separator, what can you do with the separator? You can't just ignore somehow the vertices in the separator or get rid of them or essentially don't count them. If we know that this size of the separator is small, we can and by small means that it should be sublinear in the size of the graph. So here we know that that's size of the graph, but here we show that, okay, this is a separator that you can remove it and the graph will be divided into equal parts, so you can do the recurse on that. At the same time, if you ignore those vertices of the separators, because their number is at most square root of k, and we have k, this is essentially a low order term, and you can just ignore them essentially. And that helps the whole things a lot, essentially. And that's the thing that we can get all these PTASs, etc. So let's go through this one. Let's see this application to independence. So, so this is a result by Lipton and Tarjan for independence set, that it has a PTAS on planar graph. I want to mention that. And then we say how you can just build on that based on bidimensionality theory. So independence set is a set of vertices with no edges in between. So we know that for planar graphs, so they obtain this result for planar graphs. We know that the optimum in planar graphs is at most n over 4. Like the vertex, there is an independent set of at least n over 4 on planar graphs. Why? Because this is a theorem that we have. Planar graphs are four colorable. This is another theorem that has been done actually by Robertson and Seymour. And I think Thomas, there were some other papers and they simplified this as well. But this is lots of case analysis as well. And this was so many case analysis that lots of them actually done by computer, the original versions. I don't know whether there is a computer independent proof as well or not. But so we know that it's a 4-color theorem. It means that a planar graph can be colored by 4 colors, such that no two vertices that are adjacent have the same color. This says that the size of the independence set in a planar graph should be at least n over 4. Because you just take one of these colors. Each of these colors would be independent set, so if you take the maximum of them, it would be at least n over 4. So here, so we have a constant factor approximation essentially for this problem, because you just 4-color the graph and then you take the one that has the maximum. Here I want to get, there is a 1 plus epsilon approximation for any constant epsilon greater. Idea. So this is the idea that I mentioned. So you try to use the separator theorem, as I mentioned. So for planar graph or H-minor free graphs in general, there is a separator of size square root of n. I will break this graph, and then the issue is that I will separate this graph. So I will consider this one, and then this is 2/3. Each of them is at most 2/3. The size of him is at most 2/3. The size of this separator is a square root of n. What do? I will essentially ignore this part. I said that, okay, I will just put it in the trash, essentially. Discard this set of square root of n. And then I will recurse on these people. I will do it until the size of the independent set, the size of these people that are size of this graph. So I will again find the separator vertex here and then ignore those vertices until the graph that I will get, all of them have constant size. Good. So this is the algorithm. Find the separator, get rid of the vertices. Again, on each of these components, I know that essentially the size is going at least by constant factor down. So the depth of recursion would be a square root of, would be log n. Just go there, find the separator, get rid of that, or discard it. Do that until the size of each of these components that you will have it is just constant. What do you do on that one? Find an independent set there and take the union. So essentially, you will do that. You will take the union of independent sets of constant size graph. Good. So, good. So again, find the separator, discard it, and recurse until the time that the size of each of these graphs is just constant. For some constant, this constant essentially depends on the epsilon that you want. You will go there, and on those things, you just find the independence set. Now, because the size of them is constant, then the running time to obtain the independence set would be constant as well. You will do that and take the union of all of them, and that's the independence set that they report, and I want to say that this is 1 plus epsilon. Actually, you don't need to, so as I mentioned, so this constant, you can do that, but you don't need to go to all the way to constant. You will go all the way until log n essentially. So you will go essentially all the way until the size becomes log n. And that one, so you will go essentially all the way to size of them becomes log n. Why log n is enough? Because again, if the graph size is log n, then you can find the maximum independence set in polynomial time. How come? Just try all possibilities. So there are log n vertices. So the independence set, I mean, there are 2 to the log n number of subsets of the vertices, and see which one is independent set and take the maximum. So you will go there actually up to when the size of this becomes log n. As I mentioned, then each of these components, you are solving it individually and then take the union of everything. Now, consider the whole thing as a laminar family, as we discussed. So this is the whole graph, and then this is part of the graph. This is some separator part that you want to essentially discard, and then you will continue. And then say the level 0 are the leaves. Now I want to give you a whole proof that why we get this kind of PTAS essentially. So level 0 this is the level 0. Good. So application to the independence. So this is the whole proof. I think this is one of the beautiful proofs actually that it helps to get very good ideas about these approaches that the people have used it here. And then I can give you what are the ideas when you get used bidimensionality. So this one, I mean, we are just using for independent set. For independent set, we know that so we are just using the trivial fact that there is a separator of size square root of n essentially graph on this planar graph for H1F. So we know that the maximum number of levels in this recursion that we are doing, it would be log n on base 3/2. Why? Because at each time we know that the size of each of these components that we will get, it would be at most 2/3 n. That would be less than or equal to 2. Okay. So what do we do here? So the thing that we are doing, we are considering this separator, and let's see with the union of all separators or ignored or discarded vertices. So you will consider essentially all separator vertices that we just get rid of them at some point. We want to say that the size of C is small. In particular, we want to say that the size of E is much, much smaller than N. Why? Because these are the vertices that potentially in an optimal independence set may use them. And maybe actually the independent set is exactly this set of separator vertices. If the size of them is large and we are discarding a lot of vertices, then we are in a bad shape. So, and this, good. So another interesting thing is that, what do we do here? So the thing that we are doing, we are considering this, consider this C, which is the union of all these vertex separators. So this is the whole C. Then we remove that, then what will remain? These are these graphs. that the size of each of them is at most like. These are essentially the graphs. We broke the graph into this smaller set, so the size of them is like. Now, as I mentioned, on each of them, we can find the independent set in essentially in 2 to the log n time, which is ordered, so it is polynomial. And we know that here, this is important. So for each of them, we are finding the independent set here, and we take the union. We know that optimum, so this is the important thing. So optimum may choose a set of vertices into this in this component that the size of them each of them is log n. So that this is optimum. But we know that so this is a C, so this is, say, call it V minus C. We know that size of, and here for now we are considering unweighted graph. We know that opt intersection V minus C, the size of it is less than or equal to the alg. So what does it say? It says that the optimum that you obtain here, so an optimum, I mean, has some vertices probably in C and some vertices in V minus. I know that the optimum intersection V minus C is always less than the solution that I find. Why? Because optimum restricted to V minus C is an independent set. And my algorithm on these things is actually the optimal. So optimum would be a independent set, but my solution would be the optimum independent set. Why? Because this is the best that I can do. These are the connected components that they don't have any edges to each other. So what would be the optimum for this is that you will find the optimum for each of them and take the union. And I will doing exactly that. It's because the size of this is at most log n. I can afford to pay polynomial time and then take the union of essentially all these solutions. So I know that the opt intersection V minus C is at most the alg size. So I am fine essentially in the V minus C side, and I'm competitive with opt. The only part that I may lose those vertices in opt essentially on C. And to show that, I need to see that C is very small essentially. If I show that, then I am done essentially. So this is the way that we are essentially arguing that. So now to bound the size of C. So let's K1, K2, and KL be the size of essentially components at some level I greater than or equal to 1. So what is this one? So here, this is, let me actually recording this. Good. Now, okay. So here, let's. This is the level 0 would be the last version. So this is the thing that we have obtained. So these are the things here. So this would be K1. Then it would be this is the laminar family. So this K equal to 1. This is K equal to 2, and so on and so forth. Good. So let essentially K1 to K2 to KL be the size of the sizes would be N1, N2 to NL. And these are the components of some level I greater than 1. So these are the components that we have. On each of these components, we are finding actually a separator. But here, just say the sum of the size of the component that we have it at this level of this. And again, this is laminar. We know that the number of vertices added to C, so how much we are adding. So in this one, in each of them, we are finding some small separators here, and then we discard it. So I want to see in each level how much vertices I will add it to C. So that would be essentially, if the size of this one is, and here is the, as I mentioned, it will be the size of these components, essentially. You can show that the size of these components in the worst case essentially happens that, I mean, all of them is just one component. And in that case, because of the separator theorem, I know that this would be at most a square root of the size of this at each level. I know that here, L is at most 2/3 to the I minus 1 over epsilon. Well, and note that L is essentially, so in the last level, essentially, we are L, so L starts from here. So this is L equal to 1, essentially, L equal to 2, and so on and so forth. So over all levels, this is the things. And I know that, okay, so one important thing is that I know that L is at most this amount. Why? Because I know that L would be less than or equal to n over 3 over 2 I to the minus 1 epsilon n. So I know that each of these people essentially, so I know that the size of each of these guys, I will stop it when the size of this one becomes epsilon n, which is equal to log n. So epsilon actually would be log n over n. Here is this case. So because I know that the size of each of these ones would be epsilon n, I know that when you go from each level up, the sizes goes by a factor 3.5 more. Why? Because we know that when you remove a separator, then the sizes goes down by a factor 2. So I know that each of these sets essentially have size at least epsilon n. It means that the level above them would be 3.5 times epsilon. And the other one would be 3.5 to the 2 over epsilon. So I know that how many essentially, that I know that. And I know that essentially, yeah. So this is the, then how many things do I have here? Good. So one thing that I wanted to actually fix it here. So I think I need to correct it. So here we consider C essentially to be a union of all these cuts. Here, let's K1, K2, and KL. This would be the, the components at some level are equal to 1. So this one that I have mentioned was not completely correct. So actually this was, so just, these are the L1 that are correct, but this was not the correct thing. So here, this is the one that I'm saying. So this is K1. This is K2. This is K3, and so on. So I will consider a level I. So this is the level I. I will consider a particular level I, and for this particular level I will just name the component K1, K2 to KL for some L. Now, what do I do on each of them? I will find the separator and I will add the separator to the essentially C. I want to bound how much I will lose doing it for this level I, and then I will sum it up over different I's. So far we are just focusing on particular level I. Good. Now, for this particular level I, we are this some constant times square root of nj. Nj was, so n1 was the size of the first component. So essentially n1 was was the size of k1. And n2 was the size of k2 and so on and so forth. Good. Now, as I mentioned, so this thing that I have mentioned about L is the number of, so L is the number of connected components that I have here. As I mentioned, I know that because it is the level I, the size of each of these connected components is at least 3/2 to the I minus 1 times epsilon over n. Because we are stopping at epsilon n, and then each level we go up from 0, level comes from down, essentially from bottom to top, then the size goes by at least 3/2. So we know that the size of each component, so the size of each component is at least this. They mentioned it. So how many components can I have? It would be at most L, which is less than n times the size of the connected components. That if you simplify, n will cancel out, and then essentially I will get L this formula. And again, so I will do this one. I will do it until the size of them becomes epsilon n, and this epsilon n would be equal to log n. So epsilon would be essentially log n over n. Now, this is the first one. The second one is that I know that some of these nj's, some of these sizes of these vertices in this one would be at most n. That's why also I know that, because this is any level, and any level, the number of vertices would be at most n. Now, having these two things, I want to minimize this. Essentially, I want to maximize this sum. How much I can add the maximum to this C, which is the union of all separators. For a fixed L, this sum, subject to these things, that sum of these nj is less than or equal to n, is maximized by setting all of them are equal. This happens a lot, essentially. When we have this kind of convex or concave function, you can find min and max. Generally, one good example is the case that you can prove it actually. This one, the worst case will happen when the size of all of these components will be essentially the same. In particular, would be n over L. Here I have, okay, so this is the n over L would be the size of this. I want to bound this. And here I had a bound, so I had also the estimate for L. So now I have this one, so I just sum it up. So this would be at most, when each of them is size at most n over L. So I have L of them, which, so essentially I have L of these guys, and the size of each of them is n over L. And then if you do it, that would be essentially this would be at most essentially this square root of n over L, and then I will put L the value, and that would be this essentially. So that's essentially for one level. So for one level, I can show that this, and this is I just related for level I. So that would be essentially n square root of n over epsilon times these things. Now, if I sum it up over all levels I, essentially say I equal to 1 to infinity, if you do that, then you can say that this would be essentially square root of n over epsilon times this one. But this one is the geometric sum that will be essentially this 2/3 to this, that would be at most 1 essentially. So it means that everything becomes square root of n over epsilon. Good. So so that was it. So the total number of, so this was the issue. The issue is that, I mean, when we consider opt, I knew that it has some vertices in C and some vertices in V minus C. I knew that in the intersection of v minus c, I will find the optimum. So I will be better than opt essentially in this case. The only problem is with c, and now I will say that the whole size of c is at most square root of essentially n over epsilon. Now, I took epsilon to be log n over n. So epsilon n is equal to log n. And as I mentioned, I mean, this was important that on each of them, I can find the optimum solution in 2 to the log n, which is order n. Now, what is the total number of ignored vertices? So I want to see that C was a small essentially. The total number of ignored vertices in this case, so I know that, n over epsilon, if you, so here, if you do it, yeah, so n over square root of log n. Okay, so here, I mean, the total number of vertices that I essentially ignored would be, so what is the total number of vertices? So it would be, so I will just put epsilon this value. So if I put epsilon this value, which is essentially this one, in this equation, the total number of vertices that I have ignored would be n over square root of log n. And this is epsilon prime, which is less than epsilon primes times n over 4. So here, as I mentioned, so the total number of vertices in C would be order n over epsilon. Epsilon is from this, I put epsilon equal to log n over n. And then if you put this one, then you get the total number of vertices would be n over square root of log n. And of course, n over square root of log n is less than, this is little O of n. So this is the whole idea, is that this is little O of n. So n over any function of n would be little O of n, and this one would be less than epsilon times n over 4 for enough small epsilon. And I knew that opt is at least n over 4. So I knew that the total thing that I have ignored would be at most epsilon prime times opt. So it means that essentially I have a PTAS for this problem, because all these vertices that from C that I ignored is at most form epsilon prime times up for some constant epsilon. So, and the rest I'm competitive with the optimum. This is the only part that I just ignored it. Optimum may get some vertices there, but they are not that large. The total number of vertices here would be at most epsilon prime up. Good. So this is the algorithm that I wanted to go through that for independence, such that we have an idea that how can we do this one for independence. Independence set is a maximization problem. And the good thing here is that like this was there before essentially by dimension. But there are some components that, I mean, this, here we know that independence set for this graph is at least like linear in n. And that helped us because when we try to talk about the separator theorem was also talking about there is a separator of size square root of n. N is the number of vertices. However, now think about minimization problem. For example, about vertex cover or dominating set or feedback vertex. So here, a graph, a planar graph here, I want to use essentially the separator theorem. So here, this is a star. This star has the vertex cover of size 1. Good. So for this kind of minimization problems, I cannot use this separator theorem because as soon as I say, okay, yes, there is a separator of size square root of n, but square root of n is much, much more than this one vertex optimum solution that I have. So essentially here square root, so for minimizations, so for minimization, square root of n is just too much. And so this algorithm that I have mentioned, so this is like the, using this separator approach, actually we could get for some kind of H minor free, etc. That was generalization, but for planar graph was already there essentially. And as I mentioned, this parameter Treewidth bound gives some separators in terms of opt and not n. That's the whole idea. So here for the independence set, we knew that there's a separator of size square root of n, and we could compare that one with opt. This was the place that the last line we were comparing that one with. But for minimization problem, the size of the solution can be 1. The parameter k can be 1. And the square root of n is just too much. That's the part that the bidimensionality helps us. So here we knew that the parameter Treewidth bound gives us separators which are in terms of k and not opt. So what's the meaning of that? It says that this theorem, because this, for example, vertex cover or dominating set, or I don't know, this feedback vertex set, these are bidimensional things. So we know that there is a Treewidth of these graphs. So the Treewidth is at most square root of k. When the Treewidth is the square root of k, as I mentioned, then you can say that the size of, there is a vertex separator of size square root of k. So that is very helpful now. Why? Because all these equations that I have written it here, everything was in terms of n. But now I have a Treewidth that its size is at most square root of k. And k is the size of the solution. Square root of k, square root of n is too large comparing to k. But square root of k is not large comparing to k. So I can afford to put all, again, the same thing. All these separators, I can afford to ignore them now. Because before, the theorem was not strong enough. It's talking about square root of n. Now it's talking that, okay, if the size of this things is k, then the size of the separators are square root of k. So the same equation that I have written it here in terms of n, now I can write it in terms of k. That was one thing that helps. The other issue, there was another part. The other part was that we were essentially continuing these things until when? Until the size of these graphs becomes log n. Here, the catch is that in this bidimensionality, so we cannot essentially, log n might be essentially too much for us to go there. The size might be still much larger. That's the part that we are using fixed parameter algorithms. I'm continuing this not until the size of each component become like constant or log n. I will continue until the solution size of each component becomes constant or say log k. The size of the graph might be very large here. But I know that the solution would be at most, say, constant or log k. Now, essentially, again, so this is the addition. So I mentioned that, if you remember, I had this property that here there should be let me see. Okay, yeah. So here I had this one that so so there is a 1 plus epsilon approximation with running time for this one, just computable in this one. And I had this one that there should be essentially this fixed parameter algorithm that can solve this problem, this h of. This is important here exactly because of this reason that I have mentioned. So here, first, instead of using the separator of the general graph, I will use the separator that I obtained from this bidimensionality, which is much smaller. I can afford to ignore them or discard. Then I cannot go all the way down to size, essentially constant size or log n size. I can afford to go until the size of the parameter becomes small. Because when the size of the parameter is small, even though the the whole thing is not small, the whole graph is not small, I can use my fixed parameter algorithm to find the optimum solution on each of them and possibly take the union effect. Then the question is that there was another conditions that I needed to have here. What was the other conditions? The other thing was that there should be order one approximable or order log n, as I mentioned, approximable thing in polynomial time. Why did I need that? The thing that I need is here. So here I want to come down such that the size of each parameter. So the size of this should be small. The size of, instead of log n, it should be say log k, for example. So I know that I want to make sure that the solution size is small. How can I make sure that the solution size is small on these things? Because here, it is the idea. I'm using this approximation algorithm. I know that say there's a constant factor approximation algorithm. I don't need to actually have the so the way that I understand that at this point, the size of k is small is just by using my approximation algorithms. I just run that approximation algorithm on this connected components, and really a constant factor is not important. So that can tell me when should I stop. So that essentially guides me when I should stop. And finally, last but not least, this is this one. So this is the other thing that it should have some separation property. Where do I use the separation property? Separation property is that essentially I had this idea that if these separators, if I take union of them or I ignore them, by ignoring those guys, the solution size will change at most by the size of the separator. So as long as I can bound the size of the separator, the solution size also will not change that much. So these are exactly the things that I needed essentially for this one. I need bidimensionality to get that separator size is small. I needed this fixed parameter algorithm such that when the solution size becomes small and not necessarily the size of the graph, then I can stop there and then I just use this algorithm to find the optimum solution. I need this order one approximable thing to tell me when should I stop, because this graph has a large size. How do I know that the parameter is small? I will just use order one approximation to say, oh, this is a small size, I can stop there. And finally, this separation property is the one that tells me that, okay, if you ignore the separators, the solution size of the whole graph will not change that much. So these are all three parameters that I needed exactly because of it. And this satisfies essentially for almost all of these parameters that I have mentioned. So for feedback vertex set, for dominating set, for vertex cover, for all of them, now I can get a PTAS using this approach. So this is the generalization of Lipton and Tarjan. Good. So for planar graphs, actually, there are two approaches to get a PTAS. One is the Lipton-Tarjan separator theorem. The other one was the Baker that we will talk next, which are the other one, which is called simplifying decompositions. So in the separator decomposition, I had this thing that I have this kind of small separators, and then I had do it recursively until I have small pieces, or more generally, as I mentioned, a small parameter. Instead of pieces, you can say a small parameter. Such that I can generalize it using this fixed parameter algorithm. In the simplifying decomposition, it is completely different approach. And here, you are having some simple pieces. What's the meaning of that? You decompose this graph is not like this, that you have this kind of a small size or a small parameter. You have a very large graph, but you know that the structure of each of these graphs are somehow, they are very structured. In particular, they are bounded Treewidths, or like some versions of bounded Treewidths, but they may have a very large intersection. So in that sense, these are two different approaches. Interestingly, because as I have mentioned, bidimensionality is the one that connects these two approaches, that seemingly there are two different approaches, but that connects them. Why? Because essentially comes from the fact that the diameter is also a bidimensional. So, and interestingly, so the diameter of a grid, what is the diameter of R by R grid? Actually is R. So this is one function that here f of R is actually R, not R squared. But this is the important thing. So this fact that this diameter is actually bidimensional. And this fact helped me actually to connect on the background, essentially, these two approaches and show that these two approaches actually are coming from the same thing. They seem completely different, but they have connections to the bidimensional. So today I talk essentially about the separator approach, and so Lipton and Tarjan and the generalization by dimensionality. Next time I will talk about this simplifying decomposition, that we have some interesting things. And again, they are connected to bidimensionality, but still they have different implications for some problems. And then we will go from there. So I am stopping here now.